So yesterday we were having dinner with one of the speakers tomorrow, and he was mentioning that, well, somebody was asking, oh, but so everything is machine learning, is always regularization. Well, no, it's not. It's just that here around Genova, and in fact around Boston too, we kind of feel regularization is the right point of view to look at things and get a grasp of what's common and what's different. So the way both this class and the one MIT and all the other classes we teach are tailored is so that you kind of get this principle of this story that kind of repeats itself, where you have data, then you believe it, but not too much, and you have ways of doing it, and you kind of have this framework of mind thinking about the way you should solve the problem. So I'm saying this because one thing that I hope you will appreciate as we go on, even in this short course, is that we kind of build on what we introduced, okay? We see a set of ideas, then you see that we try to build on top of them, we enlarge them, we make them richer, but you kind of see the same tools made a bit richer each time, with some twist, with some new turns, but kind of a similar set of ideas. One leap we're going to take today is to move from the usual supervised regression or classification to something more complicated. Just to mention two examples, there are two examples of things that we mentioned in the first class, and these were the case of you still have regression, but the output is going to be not one number, but a collection of numbers for each input. This is what you might call vector-valued regression or multivariate regression. The other case, which is a bit more complicated, and it turned out that the way it is posed in practice is very related to vector-valued regression, is multi-class classification. This problem is the one where rather than just two possibilities, you have T of them. And it's arguably one of the most common problems. Binary classification is just a toy problem to some extent. Most problems really have multiple options in them. So both these problems can be seen as a big superset and a super duper general problem, which, you know, I write it here in some notation with a bunch of indices, but really, if you think a bit about it, this is just take not one learning problem, but T learning problems, okay? Just T of them. Each of these learning problems is one of those that we discussed yesterday and this morning, okay? But now you have T of them. In its more wild generality, this setting can differ in everything, right? The input space can be different, the output space can be different, the probability distribution could be different, everything could be different. But you have T problems. Now, the idea is that, and this is really an artificial intelligence idea, if you want, is that this is the idea of like learning to learn, okay? The idea is that we solve a problem, and then as we solve a problem, we also learn how to solve another problem. And maybe we have two problems, we can solve them at once, and we do a better job. Luckily, not all the problems we have in life are unrelated. So once we know how to solve some, we also know how to solve some others. Or if we have two problems, maybe if we look at the commonalities between the two problems, we can solve each individual problems in a better way. See, this is just a very general principle, okay? If you want this, it's reminding a bit of when we say, oh, things are not really high-dimensional, they're related, okay? So here we're saying, well, life is not a list of independent, completely decoupled learning problems. Some of them are somewhat related. So the idea is that we can try to leverage the connection between this problem. Let's begin by notice, and I'm mostly going to stick to it because of simplicity, that vector-valued regression is just a special case of multitask learning. Let's convince ourselves of this fact for 1 minute, because then I'm going to stick to vector-valued regression for a while. So in multitask, you have many problems, each one different inputs and different outputs, okay? Consider the case where these different problems, in fact, have the same inputs. Same kind and same inputs, and the output is always just the real numbers. It means that in some sense you can collapse all these different problems into one problem where the output is a vector. The coordinate of the vector of output can be seen as tasks. The first task is learning the first coordinate of the output vector. The second task is learning the second coordinate, a third, and we can go all the way down to T. Does it make sense? So vector-valued regression is the special case of multitask learning where the inputs are the same. As I mentioned already, we'll see that multi-class will be essentially reduced to vector-valued regression. So what is the basic intuition of why multitask learning can be useful? This is perhaps a slightly extreme toy example on when multitask learning is useful. So the idea is that you have to learn the first curve, okay? And you're given the dots, the 3 dots, the input points and the output points. You have the 3 white dots in the first curve, and that's all you have. That's task 1. And I ask you, produce a good function approximation. Then I give you the second training set, task 2, where I give you the other 3 dots. Okay? And suppose that you just stare at the curve above for 1 second, and imagine you give it to any training set. Any learning algorithm, reasonable learning algorithm. What kind of prediction, what kind of function approximation is going to give you? Well, probably it's going to be flattish around here because there's nothing. Then it goes up here, do a turn, and then it's probably going to go flat again. Because where it doesn't have information, it just says 0. Okay? Here, kind of the opposite. It goes up, and then it goes down, and then it keeps on going down. Suppose that now I tell you that these two are exactly the same problem. Just perversely, I took the 2 training sets, and one training set, and I split it in 2. Then what would you do? You would put them back, say that this is just 1 training set. Now you have this data here, and now you get a much better curve that kind of looks like one of these dotted, dashed curves that I wrote, right? So this is the extreme case where the 2 problems are perfectly the same. In between, there are all the situations where we say these problems are maybe not perfectly the same, but they're kind of the same. They're very much related, okay? So clearly the key word here is related. What do we mean by related, okay? This idea that by assuming relatedness of problem, we can solve them better is going to be the whole key of multitask learning. So here it should be pretty obvious, okay? Think of solving this problem in isolation. Think of solving this problem in isolation. Think of now having a way to put them and solve them at the same time, explaining the algorithm that these 2 problems are in fact somewhat related, okay? It's clear that the last approach would be the best. So the question of this class is, okay, how do we do that? It seems interesting, but how do you do that, okay? And we want to point at the progress and the limits in trying to solve this problem. This is actually, it kind of looks like the one I just showed you. It's real data, okay? I don't remember what it is. I stole it from some papers. I think it's somebody that has to measure, say, something in the blood every day. So some people are better in doing it in certain hours of the day. Some people are better to use in some other hours of the day. But we assume that all of the people are more or less the same. So, I don't know. Glucose or iron concentration, okay? You have different people, they do all the measurements, and you would like to be able to regulate, to find out what's the pattern. And so what you try to do is to look at all the people at once and try to put them all together. Clearly you see that the effect is going to be dramatic when each individual task is going to have not so many points. Okay? If you start to have a pretty good coverage of the whole thing, the effect is going to be much less dramatic. Now, the problem of multitask learning has tons of applications and tons of different names, okay? It's depending on the field you come from, you call it conjoint learning or conjoint analysis, transfer learning, collaborative filtering, Kriging, or rather co-Kriging. This latter is the name of that is used in geophysics, where the problem of learning a vector field is very, very common. And this is just all the subset of problems. Again, the classical example of vector-valued regression is the problem where you have to estimate the vector field, which means that, say, in this case, what's the input and what's the output? Well, I think this was some fluid, okay, incompressible fluid moving in a medium, and what you have to estimate is the velocity at each point. So you sample it. The input is what? The location, and in this case it's two numbers, and then you have to estimate the velocity, okay, which is itself a vector. And now to each location you have to associate the velocity vector, which is again is two components, okay? Now think about it, okay? This is clearly, again, you can, what are the two tasks here? Each component of the velocity, okay? It's an sanity check. Usually my questions are not particularly interesting. Look now at the same plot I showed you before, but in the case of vector-valued regression, what's different? That in this case, it's not like I have different coverage of the input space. In fact, I have the same inputs, right? It's just that for each input, I have two outputs. This is a bit of an extreme case. What you see is that the inputs are exactly the same, but the outputs are slightly different. In the extreme case where you assume that the two components are just the same, what you see that the real advantage here is going to be in averaging the noise, okay? Because it's like having two observations at the same location. And in this case, for example, I draw it so that you see that this one is going down, this is going up. Now you average those, and so you might get a better estimate. It's pretty clear that the effect here, depending on the noise level and the shape of the function, but it's typically much less dramatic than in the multitask case where you really have different inputs for each task. Okay? So this is just to say these are all multitask problems, but they're not all equal. In some cases, you can expect bigger or smaller effects. So our goal today is going to be essentially try to devise a regularization framework not to devise, we're just going to discuss it. It was already devised by somebody else to us, to look at some of these problems. As we did the first couple of classes, we're mostly going to stick to linear models, okay? So each task, each component is going to be just learning a linear function. And then we're going to try to write down an error term that keeps into account all the error term all the function at once, and a penalty that is going to try to look at, again, all the functions at once. Does that make sense? In fact, it's going to turn out, what I'm going to show you is that we're going to be pretty naive on the error term. We're not going to be smart there. We're going to do something simple. And then we're going to try to be a bit smarter on the penalization, on the regularization. So for the most of this presentation, I'm actually going to stick to just penalization. But then it turns out that you can extend many ideas to other forms of regularization, such as projection regularization or early stopping. As I told you, for the case of for the error, we're just going to be simple. And we're just basically going to take the empirical error for each task separately and then sum them up. Okay? Not particularly smart. We're just going to sum up the errors. I'm mostly going to discuss the square loss, just for the sake of simplicity and for the sake of notation. You could use other loss functions. And of course, this is by no means the only choice. You could also try to couple these different error terms, right? For example, with weights. But we're not going to do that. We're just going to put all our interesting stuff in the regularization. So I'm also going to restrict myself primarily to vector-valued regression, because to some extent it's easier to present and it's more elementary. Most of the ideas can be extended to general multitask learning, okay? And we're going to mention that at the end. Again, in the case of vector-valued regression, the inputs are the same for all the output. So if you look at this expression, the only difference from before is that here xi doesn't depend on t. It doesn't change with the tasks. It's the same for all tasks, okay? So let's go back. It's like the settimana enigmistica, spot the differences. So here you see that there is a I, okay? That is the fact that each input can be different for each task. Whereas here, sort of from a perverse change of notation, there is still the I, but now it's what we called J before. And there is no task dependence, okay? So it's the same for all the tasks. As we did before, we can write things using some kind of linear algebra notation. is a little more complicated, but it's going to be a compact notation that is useful to use without writing sums all the time. It's kind of look as before. So you have x, w, and y, and you have a squared norm. But now, the vector of outputs, okay, is no longer a vector. It's actually a matrix, because now you have that each output is a vector, okay? And now you have many of them, and you stack them one on top of each other. So what is the size of the output matrix? Well, you have n examples, and each of them is of size t. The input matrix is still the same, is nd. The w is not going to be a vector, but a collection of vectors, which are size d times t. The norm there is just a compact way to write this, and it's what is called the Frobenius norm. So you can check, which is defined just that given a matrix W is defined as the trace of W transpose W, and you can check that this, if you expand this expression for W, replacing W with this quantity, you get exactly that. Okay? So this part is not so important, just we're going to use this compact notation, so x, w minus y, or just remember that now we have vectors rather than matrices, and the norm is a bit more complicated. Again, the one thing you should remember when you see this is that while it looks like now we are learning a matrix, which is all the W, really there is no coupling between the different Ws, okay? There is no coupling between the different tasks. We just wrote them in one compact notation. What we want to do is to be smart, or let's say smarter, on the way we design the penalization. So we would like to find a way to couple the task solution and do exactly what we saw in the first plot. In the first plot, the idea, you remember, the idea was on the one hand, we had things were completely unrelated or things were the same, and then we wanted to do something in between that somewhat encoded the intuitive idea of class or tasks relatedness or structure. So let's start from one choice, okay, which is the basic choice. You just take the penalization to be the sums of the squared norms of the coefficients of each component. Sorry, of the vector corresponding to each task. Okay? Is this a good choice or not? This is one choice, right? I'm taking each task, W1, W2, WT, I take the norm of each task and I sum them up. Do you like it or not? Not much. Why not? What? Because, again, it's just a sum. There is no coupling between any of the W's, okay? And this is indeed the case. If you now rewrite this, okay? You write the minimum over W1, WT of the sum of the error plus this. But now what you can do is that there is really no coupling of the W's. So what you can do is that you can put the sum outside and move the minimum inside and do each minimum separately. So this is like the single task approach to multitask learning, which is basically disregarding the multitask structure and just solving each problem separately, completely. All right? So this is going to be the starting point of what we don't want to do. This is the first way to try to enforce class relatedness, okay? The notation is a bit more complex, but let's read it. The first, so it's a convex sum of two terms, okay? You say you have one term, another sum, and you want to sum them up with weights that sum up to 1. So alpha and 1 minus alpha. The first term is just the same as before. So you just say each task should be regularized. What is this doing? How does this look like? What does it remind you of? Variance. Of what? Variance of vectors is not rewarding enough as an answer. It's a variance, okay, of what? Of each task with respect to the average, sorry? Yeah, the average, say the average, he said the average weight for all the tasks, let's say the average task, okay? So you're basically saying that it's really similar to the one plot I showed at the beginning. You're basically saying the curve are in fact kind of all looking like the same curve plus some perturbation which is specific for each curve separately, okay? So you say, I have all these different problems, all of them should be simple enough, but all of them is close to a common problem. This is a first example which is something non-trivial, okay? In this case, there is class relatedness. What is that, and this is what we like in this example. What is that you don't like in this example? Assuming that you don't like something. Say it again? You have to choose alpha, sure enough. Suppose that 1/2 is fine. Well, let's put it this way. Do you think this penalty is going to be good for any multitask learning problem? Probably not. Why not? Well, suppose for a minute that I call this the isotropic coupling, which means that everybody is coupled in a same way. So this suggests that perhaps you would like to do a non-isotropic, which means that maybe not all the tasks are just the same as similar to one. So for example, what might happen? Well, some tasks might be divided in groups. I have groups of tasks, and each one is similar to its own average task, but there are groups, okay? So I don't even write it, but you can imagine how you can write it down. This will be another penalty. You have to know the groups, and once you have the groups, you write exactly this, and you sum up over the groups. Only the average task will be the average task of each group, okay? More generally, what you can think of is to do something like this. It's what I call the graph coupling. The idea is that I give you the tasks. In the first case, I tell you that everybody is similar or unsimilar as in the same way. In the second case, I give you clusters. In this last case, I tell you that I give you a graph that tells you who's related to who. Okay? The graph is a graph describing the task's structure. And then I try to design a penalty based on this graph. How do you do that? Well, what's written here is, again, I penalize each task. Each task should be simple enough, okay? Then what I say is that each task should be close to another task, and how close they are depends on how much they are connected in the graph describing the task relatedness. So if two tasks are very close in the graph, or they have a strong, this is a weighted graph, okay? So M is a weighted, it's an adjacency matrix with the weights. So if you have big weights, it means that these two tasks are really, really similar. If you instead have that they're very far away on the graph, or they're not connected, then you don't ask them to be similar. Make sense? So this is a much richer way of relating things. Notice that in all these cases, we're going to discuss it in a little bit, we are assuming the structure to be known, okay? So for the time being, we assume that somebody gives us the groups, the graphs, or whatever it is that describe the task relatedness. And we just ask how to exploit it. And we actually just answered that question, because this is how you do it. You have the empirical risk, and now you have the penalization. Now, the next question is what? Say it again? Right, so let's say there is a big question, and we postpone always the good question later on. So the good question is, how do you estimate M? Okay? But for the time being, we're actually going to ask a simpler question, which is, suppose that you pick one of these penalty, how do you solve the corresponding optimization problem? Is this an easy question or a complicated question? Somebody says easy. Why does it look reasonably easy? Well, because we are taking the square loss, this is the square norm, everything looks the same. But yet these two things look similar, but not that similar. It looks like each time you have to do something different. So let's think a second if all these examples can actually be seen as special cases of some general idea. And then we can think of solving that general idea. So in fact, what you can see, and you can see it from here, you know, look at this stuff. This is all sum of products, right? Here you take the product of Wj with itself. Here you take the product Wj with some other stuff, okay? And you have a bunch of terms. You got a long list, okay? And these products have some weights in front of them. Here is simpler, here will depend on the adjacency matrix, right? So this, you just have a bunch of products. So it turns out that this is exactly the shape of all the penalties you've seen so far. They all share the fact that they're just the sum over all possible tasks of the inner product of the weights between the two tasks, weighted for some matrix A. A is a matrix that encodes the structure that we're assuming on the problem. So we can play now a game and say, okay, what is A for the various examples we showed? The first case is this guy, the single task, completely unrelated tasks, okay? And it's easy to see, well, but put too much emphasis on this, it's very easy to see that A is just the identity. Okay? So everybody is just related to himself and completely unrelated to everybody else. It's an identity, there is zero of the diagonal. Nobody is related with anybody else. The second example, this one here, you can check that the A is given by the identity minus some factor, and then the matrix of all ones. Okay? So this thing here is just a matrix, which is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. The matrix of all ones. Suppose that here we don't put. We don't put this term. The matrix of all ones corresponds to what? Is the other extreme case. In this case, all the tasks are completely unrelated. If I were to put the matrix of all ones, this would be like assuming that the tasks are just one task. Okay, they're all just the same task. So here, basically, this says, oh, my structure matrix is an interpolation, is a convex combination between the single task and the one task. Okay, so it makes sense. This matrix is meaningful in its own right. Rather than thinking in terms of penalizers or regularizations, we can think in terms of this matrix. Or you can keep on going, and you can check that if you write down the matrix A corresponding to this, is actually given by a matrix that you kind of are happy to meet when you talk about graphs, which is just the graph Laplacian, okay? And here I remind you the definition, which is basically take the matrix of weights, okay, the adjacency matrix, sum all the rows, and you get, so you take the first row, you sum, you get the number, and you put it in the first element of the diagonal. You sum the second row, you get a second number, you put it in the second element of the diagonal, and this way you get a diagonal matrix. What does it mean? If you're thinking about the graph, it means that you sit on a vertex, you look at all the incoming edges, and you sum the weights, and you get a number. And this is called the degree of the vertex of the graph. Then you jump on the next vertex over, and you do the same thing. You sum all the weights incoming in the graph. And this is this matrix D, okay? It's diagonal. You just have for each vertex the degree. The graph Laplacian is defined as the degree matrix minus the adjacency matrix itself. Carlo, you confirm. So the graph Laplacian it's nice to have it here because it's a fundamental object in the analysis of graphs. It's called the Laplacian because in some sense one can show that it shares a lot of the properties of the usual Laplace operator that we know from analysis. Okay, so it's in particular its eigenfunctions and eigenvalues have all meaning about the graphs. What we do here is just see it on a very high level, the fact that nicely enough, it turns out that the regularization that we impose on the on the task relatedness is completely governed by the graph Laplacian. All right, so we now know that all the penalties are kind of the same for a choice of structured, for structure matrix, okay? A matrix that encodes the structure. If we take a step further, it's not hard to show that this thing here can also be written in a kind of linear algebra way as the trace of W times A times W transpose, okay? And this takes a few lines to show. This is not so important. What's important that now we have this nice compact way to write a family of problems, okay? Each problem is defined by a structure matrix A, and then we have the same form of the problem. So now it's a good point, it's a good moment to ask, how do you solve this problem? Because now they all look the same, and then you kind of know how to recycle code, which is always a good thing if you don't know how to code like me. So one way to do this, okay, this turns out to be easy, but not super duper easy, okay? So one way to do it is to try to reduce this to the single task problem. The single task problem is easy, right? Let's go back to it just 1 second. If you have to solve this, how do you do that? Well, it's just each individual task, and the matrix, the input matrix is the same. So in fact, you can just solve one inversion and then apply to all the different outputs. So it's very easy, okay? So the question here is, can we reduce this, this to single task? Can we? How do we do that? And the answer is yes, almost. Change of base. Which base? Yeah. So what you do is that you say, I take A, okay, I diagonalize. Because actually I hid a little detail from you, which is that all the A that you just show are symmetric and positive definite. Okay, and that's what we're going to assume here. We could relax it to be positive semi-definite, but let's stick to positive definite so that everything is invertible. So all the matrices I show you are symmetric and positive definite, and let's assume that this matrix is also positive definite and symmetric, then I can diagonalize it. If I diagonalize it now, I could do a change of variables and try to see that what do I get. If you do that, what you see is that if you call U and sigma the eigenvectors and eigenvalues of A, what you see is that you can define a new, here you're going to get W, U, sigma, U transpose, W transpose. So you can define a new variable, W tilde, which is going to be WU. And then it turns out that you will also, if you want things to go right in here, you will also have to rotate the output matrix, okay, in some way. And then you get something that looks like this. So it's, if you see the difference between this and that, there are two things. One is that instead of W, X is the same, but W is replaced by W tilde, Y hat is replaced by Y tilde, and here rather than A, you just have sigma, which is a diagonal matrix, which means that now the trace just reduced to a sum of product of norms weighted by the element of the diagonal. Okay? So this takes, I'm skipping one step here just to check that this goes through fine. But let's just take it for granted. Now we're here. We change the variable. Eventually, in the end, we'll have to go back to the original variable. But we change the variable for now. Now we have to solve this, and we just have to rewrite it down. Well, let's do it. But this is really almost single task learning. What did you do? You take the output space, you change the basis, you rotate the basis of the output space so that the structure matrix becomes diagonal. And then what you do is that in this new basis, you solve a problem which is basically a sum of tasks, independent up to the fact that in front of the regularizer, you have a weight that depends on all the other tasks. Okay? So, that makes sense? I just rewrote this, okay? There's nothing going on in here. So the good news is that for everything that is written, defined by a matrix A, they all look the same up to the fact that you diagonalize the task matrix, okay? So this is in some sense good news. If the diagonalization of A is affordable, then you can reduce the problem to single task. Okay? Notice that in this case, maybe I should show these ones. In this case, the number of tasks basically doesn't appear. So if you do the single task, you can easily see that basically you get x transpose x plus lambda ni minus 1 x transpose. And the only difference with the scalar case is that this part is the same, okay? It's just the same. What changes in the single task case is that here, this rather than be an n by 1 is an n by t matrix. So in the single task, you have to solve this once. You have to invert it. Suppose that you do the eigendecomposition. You do the eigendecomposition of this once, and then you just apply it here. So this computation doesn't depend on the tasks, okay? It's nice. I mean, really, in general, this is not true, right? You have many tasks and so on. If you do what I hope is written there, okay, what are the differences? Is it? Yeah. You have to first diagonalize A, and this is going to cost you roughly t cube. So this does depend on the tasks. And then you plug it in here, and you cannot quite solve just one. You will have to solve one for each of these guys. Okay? If you do an eigendecomposition, it's still going to be 3. If you want to solve the problem, say, with a Cholesky decomposition, then we'll have to solve one problem for each of these different tasks. Okay? So eigendecomposition could be, if you can do it fast, could be a good choice here. So that's why we're quite happy about this. We're not so happy because this also hints at the fact that all these regularizers that kind of look interesting, you know, they're just either putting some isotropic or some anisotropic structure between all the tasks. In fact, what they're basically doing is rotating the output space and putting weights, putting regularization parameter that depends on all the others. So this is all we are doing. And this is reflected in the fact that if you want as we comment later on, the structure matrix is just inducing some linear dependence among the different tasks. You don't get something, it's just a matrix. So all the tasks are just defined, related in a linear way. Also, you see here that the task relatedness matrix A is somewhat related to how you define an inner product between the whole tasks. In some sense, you have this matrix A is related to the geometry, or how you define a geometry, an inner product, distance, and so on, in the output space. And here we're just rotating so that we just have a simple inner product that is just weighted in all the directions. All right, so this is one way of doing this. We really exploited the property of the square laws to do this. More generally, what we can do is just say, well, let's just do gradient descent, okay? We just take this, it's convex. In fact, it's strongly convex, and I just go in and just do a gradient descent. Clearly, this will extend trivially to all other loss functions you can think of. Okay, there's not. If you take a loss function which is a sum of loss functions, well, and it's reasonable enough, then you can typically do this. Okay, with little effort. Okay, same game as usual. What about going beyond linear models? Okay, same as usual. If you take a bunch of nonlinear features, you just have to change the name of the inputs, and it's the same. So at this point, this hopefully look kind of familiar. What if you look at kernels? Well, in the case of kernels, would take us a little bit to go in and make the derivation precise. So again, just appreciate the fact that you get something which is kind of what you hope for. You basically have one representer theorem per component, which means that rather than having just one vector of coefficient c, you have one vector per task, okay, per component. So now you have to estimate a matrix C. And again, you can basically do it by, for example, by gradient descent. And here I just show you that, okay? One thing that I don't show you, and this again would cost me a little bit, is to show you how you can take the idea of spectral regularization, so projection, early stopping, and so on, and use it with in this multitask setting when you have knowledge of a structure matrix A. Okay. Notice that when you get here, you are kind of a long way from how we started. The way we started was, let's just write regularizers, okay? Here we are, oh no, the important bit is a matrix A. Oh wait, I don't need regularizer at all. I could do projection or early stopping, as long as I use the right matrix A, okay? So it was useful to go down the path to understand the structure of the problem. We're going fast. We're gonna finish soon this class. Okay. So let's just stop 1 second and ponder what we did so far. We said, let's look at vector valid regression, where rather than one output, I have many. And let's first think of how to put regularizers that are going to couple the different outputs. And we pull out of our hat a few reasonable choices. The isotropic coupling, the cluster coupling, the graph coupling. And then we spend a bit of time basically showing that they can all be written in the same way. And let me show you again, because this is the main thing, and it's simple. We basically said they all have this form, and we can easily derive the different A's, and all this form can be written like this, so that in the end, we can look at this nice equation, which is kind of compact, and we can use this to think about computations. Luckily, the discussion here is fairly short, because up to the change of basis, we're back to single task stuff that we discussed the whole day yesterday, okay, and today. So there's nothing new there. So again, this is one point where hopefully you see how we abstract things a bit so that we can recycle a lot. All the interesting bit here is going into this expression and deciding how to pick A, okay? So what we want to do next is push this a bit further. Okay, so try to take further steps. One step we want to take is to look at multi-class classification and see that basically it can be reduced to this setting. Multi-class classification is just the problem where, this is my favorite slide, it's very concise. It's just one of T symbols, okay? How do we solve this problem? Well, let's kill the bad way of doing it, okay? Well, the bad way, what did we do for classification? Well, we had two symbols, and in a sense, we disregarded that, and we just treated them as numbers. We said, oh, we have 0 and 1. How about I just do regression? And then I take the sign. So the first thing you can think of, well, why don't we do the same here? I have 1 to t, and I just do regression. And I just regress these real numbers. Is this a good idea or not? No. Because? Yeah, because you put classes, so what he's saying is that by putting them in an order, you're putting things close to each other, and they're not. The number 3 and number 4 are just two numbers, and you're putting them close, and 3 is further away from 6 than 4. Why? Okay, it's completely artificial, and if you do this, this is just going to be wrong, okay? So what is the solution to this? Yeah. Well, the problem is, in some sense, you put them on the same line, whereas you would like to put them in such a way that they're all, you would like to put them somewhere in such a way that they're all distance apart in the same way, okay? And you cannot do it in just one dimension, okay? You basically have to put each of these in a corner of something so that they're all far away in the same way, for example, okay? And our friend in the second row immediately says binary coding, okay? Because he's exactly doing this. He's taking an hypercube and putting each of these in exactly far. But this is the reason, right? Because other things being equal, you don't know who's related to whom, and you would like to put them all far away. Okay, so this is a kind of obvious way to turn the problem to make our choice of encoding democratic, so we don't introduce similarity. Okay, nothing new here. So we do this encoding where each of the symbol goes into an element of the canonical basis, where the only entry different from 0 is going to be the index corresponding to the symbol. Okay, so the first is going to be 1, 0, 0, the second is 0, 1, 0, 0, and blah, blah. So clearly, at this point, each of the output is going to correspond only to, is going to correspond exactly to a vector. Okay, we had input and label, and now we're going to have input and encoding of the label, which is exactly a vector of size t. So clearly, we reduced the problem into a a vector-valid regression problem. One question is, how do you go back? Okay, suppose that now we solve a vector-valid regression problem. We have to still go back. I don't care about the vector-valid regression problem, right? I want to know which class I have. How do you go back? Well, the idea is that you have this hypercube with all this direction. Now you find your f of x, and you want to know which is the closest vertex, okay? And the way you do it is simply by doing this. Which, if you want, is you're projecting the vector on each of the vertices, and this corresponds exactly to taking the component with the biggest value. So you take ft of x, f1 of x, f2 of x, you order them and you pick the biggest one. All right, so this is one way, we pulled out one way of doing it, which is kind of the most common way. We're just rederiving it slowly to get the connection with what we discussed in the first part of the class. So how many of you have any experience with multi-class classification? What do you usually do to solve it? One versus all. Okay, the two common ones are all versus all or one versus all. The two things that you do in these cases are, you basically said, I take this class and I do this class against everybody else. Then I do the second class and I do the same. And when I get the final score, I order the scores and I pick the biggest one. Okay? Or the other one is all versus all, where you add everybody play against everybody else, and then you have to decide how you want to set up a tournament, which is a bit more complicated. Well, the first observation we make here is that if once you choose the binary encoding and you put the trivial choice of the structure matrix, you're doing exactly one versus all, okay? There's nothing else. So let's just appreciate that this is true. This is exactly the equation we stared at for a little bit. The y hat here is exactly the concatenation of the output vectors. Only here, these are special vectors because each of them is going to have just one value different from 0. Okay? And here, there is no A. There is just identity. So this is the single task. Everything is separated from everything else. Sorry, there is a Frobenius norm missing here. So there is a Frobenius pedex here. If you now rewrite this, doing exactly what we did before, what you see is, again, there are a bunch of typos. There should be no t here. It's the same x for everybody. But the important bit here is that for fixed t, you're going to have yi. And if you think about it 1 second, it means that if you fix t, which is one class, the yi are going to be such that for that class, you have 1, and for everybody else, you have 0. And because all the problems decouple, it means that you're doing each class separately, doing 1 versus everybody else. Right? So it's completely straightforward when you get here. Notice also one thing. If your goal, let's discuss something something strange that happens and that sometimes creates some confusion. Suppose that for each class you have 10 points, okay? Once you solve this problem, you have 10 points, you have 10 classes. For each class, you have 10 points, which means that for the one class, you have 10 points, and for everybody else, you have 90 points. Correct? And you solve 10 extremely unbalanced problems, where the all is much bigger than the 1. Is this an issue or not? Carlo, no. Is the question clear? I imagine it is, not too hard. So you have all these one versus all. For each of them, you have, for the one class, you have, say, 10 points. For everybody else, you have 90. So it's very unbalanced. And you solve the problem for each of them. Are you worried or not? So a bunch of you raise their hands that use all one versus all. So please let me know what you usually do. Do you care about this or not? You can check on the internet. So what do? Do you cure the imbalance or not? Let's take votes. Okay? Do you think it's a problem or not? Who thinks it's a problem? You have to take votes, which is yes or no answer. This doesn't count. Is it a problem? Who says no? What about everybody else? Thinking about focaccia. It is a problem or not? Yes. Okay, his internet said yes. So, in fact, it depends, okay? It depends what is you're trying to achieve in the end of the day. If each class, so notice two observations, okay? It's true that it's very unbalanced, but it's also true that what you do is that you take a score for each class and then you order them. You don't care if it's positive or, you order them, you rank them, okay? And as long as the ranking is fine, maybe everything can be, you may always even say all, you may always say the other class, but they're ranked. And if the ranking is fine, you're gonna say the right class, correct? You see what I'm saying? It might be that for each of these, you find the W, then when you say WTX, it's gonna say negative, which means that you take not the one class, but everybody else. But then you rank all these scores, and you're gonna pick the first one, okay? So that's fine, okay? This is the first observation. Don't be fooled. Even if they all push the boundary in the negative region, while you take the ranking, you still are gonna select one of the one classes. So this is already a little bit reassuring. Yet, you have this big unbalancing. Should you worry or not? Well, it depends. If, as you do at the beginning, you assume that each class error counts equally, and what you want to do is to minimize the error among all classes equally, okay, the average error among all classes, this is just fine. This is just fine. I mean, there is this whole symmetry in the problem. You don't want to break it. Every class counts the same. Everybody is unbalanced in the same way. When you take the ranking, you're, again, putting everything in a democratic way. So no, it's not a problem, okay? But suppose now that, for example, what happens is that either you choose that one class should pay more than another, or you have one class that really is bigger than another class. So that by not reweighting, you're effectively decided that one should pay more than the other. Then that's a problem. Then you should cure it. But not because of one versus all. Because you decided that you wanted to pay different for all the classes, or because the different classes had different size. Instead of being 1/2, they really were 2/3, 1/3. And then you have to do reweighting. Okay? So whenever you are in one of these two situations, you do want to cure the imbalance. But if all you care about is to have a nice error shared among everybody, this is just fine. There is no reason why you should change it, okay? And this is this is a point that always creates a bit of confusion, mostly because the first thing you see is this big imbalance. Say, oh, what's going on? I have to rebalance. No, in fact, no. I mean, there is no reason to do it, okay? And in practice, if you try, this is in fact true. Now, the next step, as you might imagine, is just say, well, why do you have to do one versus all? If it's just the stupidest case that we discussed in the first slide, you can try to do something else, okay? How about this? For example, here you're saying, well, my classes, my different topics in my different topics in my documents, or my different objects in the images are related depending on some graph or something else. Yeah, you can do that, and it's straightforward, okay? Of course, you have to have somebody that comes to you and provide you this taxonomy, this structure among the classes. But even that, I have to say that one of my annoying delusion in life was that when we tried to do this, we saw that the effect of introducing class relatedness in multi-class problem was way more dramatic than I hoped for. okay? The one versus all is very hard to beat, okay? There's been papers that show this, okay, empirically. But here, perhaps we can kind of grasp what's going on and why one versus all is actually pretty hard to beat. Why is it? Again, what I'm saying is, you're in multi-class classification. I give you a graph that tells you how the classes are all related. You use it. Instead of one versus all, you do one versus all, and then you do this weighted one versus all, and then you go in and check the performance of these two algorithms. And empirically, you find out that they're actually pretty similar. Why? Sorry, can you repeat?
Let's say that two classes are very close to each other and we give the same matrix, right? So at the end our model is going to give the same weights to them, right? So at the end we are not able to classify them more separately than this. So our model will say, okay, this sample belongs to this class, this one.
But why should it be worse than a single task? Why should be, you see what I'm saying? Why A should be basically doing nothing more than single task? If you take I equal identity or I different of identity, why should it be more or less the same?
I equals to I, if we and I then so all the tasks are independent. But if we are trying to make them two tasks related to each other, the model is also going to classify them into these two classes more than the others. So
this is why it should work, right? Not why it should not work. So this is why you should expect it should work better. Yeah. Yeah. So, okay, I'm going to decode that in a minute for everybody else. So everybody else has any comment on this? Why do you think these two things can work quite the same? Yeah.
Maybe because it's a problem of classification. So you don't have a lot of concept. We finally take the maximum of all this.
You what, sorry?
Finally, we take the maximum of all the results. So
Yeah. Yeah, so now let's put together all this stuff, okay? So what he's saying, so let's make 3 comments that shed some light on this apparent little gain of putting structure in multi-class problem, okay? So what he's saying is, well, you put class close together, okay? But in the end of the day, you only care about making one prediction. So yes, you make them all together, but at some point you have to commit to one of the two. And it's not clear that you make you're going to have 2 top scores close to each other, but then you still have to pick the biggest of the 2. So either they really make something nice, or it might be that the ranking remains the same. And it's kind of the point that is highlighting. In the end of the day, you're going to rank the scores. So they might be awfully wrong, but if the ranking is stable, you're good to go. Okay? This is one, 2 observations, which makes sense, right? And you see it here. That's what's going on. Also, you've seen before that the effect of multitask learning, when you put task related, was very dramatic when you have different inputs for different tasks. Whereas when you have the same input for the same task, is the one picture at the beginning is much smaller. It's basically averaging of the noise. So it's much less. And multi-class is exactly doing that. Okay, it's just a special case of vector valid regression. Finally, what you see here is that, as we pointed out before, the moment we put A, we're basically doing 2 things. One is that we are rotating the output space. But for multi-class classification, does it matter if we rotate the output space? It does not, because we're going to take, you remember that the coding is this inner product. So if you rotate everything, it doesn't matter. It just doesn't matter, okay? So the rotation itself doesn't do anything. So in A, when we chose A, the fact that we rotate doesn't matter, okay? The only thing left is the weights on the diagonal. But these are just going to change here, okay? That's all it's going to change. And now we have to wonder how much this is going to matter, okay? It turns out that what you do in practice is not to choose one lambda for, when you do one versus all, typically you keep one lambda for each of the one versus all separately, okay? You don't choose just one. It's a detail, okay? It's a small detail in the way you set it up, apparently. But when you do one versus all, you do one versus everybody else, and then you have one lambda here, you have one for all of them, and then you have some heuristic to decide how to pick it up. But then this means that basically you're not, rather than, it's in some sense is a way to learn A, or the sigmas of the A. So rather than just having the sigmas chosen and then penalizing just once, you pick one regularization parameter per class, which basically means that you're kind of doing already something like this. So it's not surprising at all. Of course, once you understand it, it's not surprising at all, that sweating to define the best possible structure actually gives you something very similar to well set up one versus all. And you really have to cheat a lot to publish papers that show that A gives a big boost. But luckily enough, we have a lot of examples you can learn from. It's really the amazing literature. The literature on this stuff is tons of papers that claims big boost on performance of, picking up the right A. But then if you set up the one versus all, when you fine-tune the lambda with cross-validation, you just get as good, okay? Carlo, you confirm. I'm a bit emphasizing this because usually we bump our head into this quite a bit, because we came with the expectation that it would give a big bump. We find a lot of paper that were claiming it, and then in the day, once you understand, you're like, no, it's quite clear that it doesn't give a big bump. You have to do something more than that, and it's an open problem. What more you can do than this? Okay? What really smart things you can do? Also, because the single task is so simple that you can really tune it well. It takes so little. Look at this equation. It's so simple. It takes really short to do it. So you have a lot of time to do all the tuning carefully. So you really have to do something smarter. And of course, there are things you can do, but not in this framework. So let me just add with a few more comments. Let's close the chapter of multi-class classification. Are there any questions about this? So yep. Yeah, we're getting there. We're getting there. So what he's saying is, going back to the question, okay, but here the structure is given. Could we try to somewhat, yeah, we get there, okay? And the answer is going to be yes, we could do something like that. Anything else? So again, the take-home message here is the obvious way to turn multi-class into, let's say, the obvious way of treat multi-class, which is one versus all, turns out to be a principled, very natural way to cast multi-class problem by choosing a coding that makes them all separated the same way and then treat them as a vector-valued regression problem. Indeed, once you're there, you can see that one versus all is just the one very special case where you treat all classes independently. Unfortunately, you also see that being smarter and try to put class relatedness might not pay off as much as you would hope for, okay, when you start your experiments. And somewhat the details, the devil is in the detail, is in the way you set up regularization parameter and the way you decode by taking just the maximum. Let me mention, because I think I had it, but it disappeared or I didn't read it. No, it's written here. That by making this observation, you're kind of also killing another line of research, which is one that says, maybe what you should do is to get a much better coding of your classes. Why 100? I think this class should be closer than this class, and no. Okay? There is actually a lot of paper doing that too. But they're not completely equivalent, but is essentially corresponding to choosing A. You can show that if you pick a different coding of your classes, which is going to be a different matrix, instead of 1, 0, 0, it's going to be a different one. This is essentially equivalent to choosing an A. But then sweat as much as you want. In the end of the day, you're going to end up with the same thing. So spending a lot of time picking an A, spending a lot of time changing the distance in the coding space or the encoding of your classes is going to be more or less, it's going to get you as far as putting some weights in front of each of the norms. Okay? So don't spend a lot of time on that. So We started with multitask. We immediately jumped to vector valued regression. We now discussed multi-class. Let's go back to multitask quickly, okay? The idea is that you can convince yourself that the original multitask, the one where the input points could be different for all different tasks, could be rewritten very similarly to what we did before, with a few differences. These two parts are almost the same. So what you do is that you take, again, now the input points are different for all the tasks. You take all the input points and you stack them on top of each other. So that's the same as before, only the number of points is going to be the sum of the number of points per task. The W is going to be still a big matrix. Y, okay, is now a matrix, but each point is going to have a value only for one task, because it's the output for only one task. So it's going to have a bunch of zeros, where all the tasks it doesn't belong to, and then for the task it belongs to, it has a number. Correct? This is the only one important bit in the whole slide, okay? The output matrix, for each point, you can build it as n by t, but truly, it's not a matrix that, in the real sense, it's a matrix full of holes, okay? You fake numbers, you can put 0 if you want, but the only one that matters is the one number for that task. Is that clear? When you write this term, you're forgetting that, okay? If you just look at this term, you're not telling it that it doesn't have to produce zeros. So if you don't put anything, you ignore this weird symbol and this M. If you just do what you were doing before, you're now regressing fake numbers that you introduced in each row of the matrix Y because you didn't know what to put. So what you need to do is to put a mask, and this is just the entry-wise product that is going to say, kill everything here and also everything here, okay? And this is equivalent to do this. So again, this is just a vector notation, just to explain how to match this to what we did before. You basically have to put a mask that say, only look at the right numbers. Notice that the part where you regularize is just the same as before, okay? Nothing changes. If you now check how to extend what we just saw from a computational perspective, the penalty is fine. You need to worry about this. And it turns out that it's not too complicated, but in some sense it's useful to tensorize this expression, to use tensor notation to rewrite this in a more convenient way. And it gets a little bit more complicated what we want to do here. But the take-home message is that the same computation that I show you for the vector valued regression case can be more or less adapted to this case. Not only that, at this point you can say, well, but my problem is huge now. My Y is huge, this huge number. Yeah, true, but it's mostly zeros, right? So this mask contains a lot of zeros. So you can exploit that to try to leverage. You can leverage that to try to reduce the amount of computations you have in your solution. Okay? And in particular, up to this tensor trick, you can do the same trick we did before with the matrix A, diagonalizing A, rotating the output space. You can do tricks like that. I'd just like to mention another problem before we finish our list of problems. If you think what we've been doing up to now in the linear case, that we've basically been learning a matrix, right? A matrix W. One of the most popular problems in the last few years has been matrix completion. It's very easy to say in words. There is a matrix, okay? I'm God, I know a matrix, and I'm going to give it to you. But before doing that, I'm going to delete entries. Or rather, I'm going to pick a few entries and I'm going to give to you. I say, entry 3544 is 3. And maybe I'm also going to put some noise in it to make your life harder. And then I say, give me back the full matrix, okay? Tell me the full matrix that I give you. This is the matrix completion problem. And, you know, people talk about Netflix years ago, blah, blah, blah. That's kind of old. But it's still a pretty basic problem, okay? It turns out that it can be related to what we've been discussing so far. And in fact, it's just a special case where what we do is that we take the dimension D and the number of points to be the same. And we take X, sorry, this is X hat, okay? Which is now an N by N or D by D matrix to be the identity. So it disappears. then you can turn out that what I just wrote just reduces to something like this. So what is written here is exactly what I was showing you, okay? You're gonna have a matrix yi, yj, but this is perhaps a bit misleading, okay? Basically, of the matrix yi, yj, I'm just gonna give you some entries. The one that correspond to the mask values different from 0. And then you have to find everybody else, all right? So this means basically that up to the change of the objective from the one we had before to this one here, which is the one where here you have the identity, you can use all the same ideas we've been using so far to the problem of matrix completion. Okay, you can penalize with this trace norm, this weighted trace norm, and do just the same. Again, the basic idea here, as you see, is that the hope, how can you hope to fill in the holes of a matrix where I don't give you entries? Well, the entries might be related to each other, right? One simple way of doing it is that you take the average of nearby entries and you put it there. Here we just give another way that basically say, well, let's assume that there is, a, for example, the rank of the matrix or the trace of the matrix is small, which basically means that the matrix looks big but is not really. Then we might have hope to fill in the numbers. And here I'm just showing you this is not unrelated. In fact, it's very related to what we discussed today. Okay, so the last bit is very complicated, but we're going to make it very simple because we're going to make it very short. What we discussed so far is vector-valued regression, multi-class, multitask, matrix completion. We kind of all see that, you know, in some sense, this is the one important equation, and everything else falls from there, okay, up to minor modification. That's what we spend a bit of time at the beginning. So it's kind of nice. I mean, this is the, you know, you kind of have, you know, a bunch of different ideas falling nicely in the same framework. But the big question has been, what if you don't know A, okay? Now, let's start with the due expectation out of this, okay? Again, for multi-class, I'm not sure this is worth it the time, because you know that at best, you're going to basically make your life hard to just choose these sigma 1, sigma t weights in front of the norms, okay? That's the best thing you can hope for, because the other rotation you're learning doesn't matter. But for other problems, for example, for multitask problem, where really you have different problem with different number of training sets and different number of, different number of training example and different input points, maybe we should learn, for example, we know that it's a graph, but we don't know the graph, or we know that this is a bunch of clusters, but we don't know the clusters, okay? Now, there is a good news and a bad news. The good news is that once I give you this with an A, and I ask you, can you learn it, okay? You can kind of say, well, how about I just add the penalty on A, and I assume that A is a positive definite matrix, and I put some penalty that should tell my data that my A should be of a reasonable form. For example, it should be a graph, say, okay? Or it should be a matrix with blocks. Now, let me skip this part, the previous slide, and basically say, there is another good news, is that once you do this, for many choices of the penalty, what you can see is that in some sense, the problem decouples, because you see W appears only here, and A appears only here, and oftentimes what you can check is that the problem is actually convex in W, and for many choices of the penalty, is also convex in A. Unfortunately, it's not convex in W and A, okay? So, even when it's not convex, what you can do is say, well, it's convex here, it's convex there, how about I just do alternative minimization? So the classical way of doing this is pick an A, then plug it in here, and optimize over W. Of course, now the fact you have pen of A fixed doesn't matter, and you just have to solve exactly the same problem I showed you before. Now you got a W, you plug it in here, this term doesn't matter, you have to solve this. Okay? And you keep on going, alternating the two. So, we worked a bit yesterday to try to see if we could tell you a bit more, but here how the story goes. Interesting enough, there are a lot of choices of the penalty for which you can reparameterize the problem and show that essentially this solving strategy converts to a global minimizer. So that's very good news, okay? A bit surprisingly, while in general this is a non-convex problem, you can in fact exploit the structure to reparameterize the problem and show that in some sense there is a hidden convexity that allows to go to a global minimizer, okay? This cost us a bit, and also we have to give several examples of penalties, okay? But so, and this is any simple version of this we tried yesterday, took us an hour, so maybe we should go to lunch. The thing we're gonna do for this is probably to send you to pointers, okay? This is very recent works, okay? This has been works in the last couple of years showing that you can do this in a good way. But so, long story short, for these problems, you can learn A, you can do it in a variational way with an approach which is kind of simple, and you can even prove it goes to a global minimizer. On Thursday, in the very last part, if we manage, we're gonna go back to this and see how we can use ideas of sparsity to kind of plug something in there and you get something reasonable, okay? And so this is basically all I wanted to say. Again, the main topic we touched upon, we went beyond scalar or classification, in this case where you have multiple outputs, and we spent some time thinking of why we want to do that, how we can do it in a regularization framework, and then discuss a bit related problems such as multi-class, multitask, and matrix completion. And multi-class for me was my favorite one in this, because it's kind of the one where I think one can learn the most with the least effort, and this saves a lot of energies later on. And lastly, we briefly, and only gave you an appetizer of how to potentially try to learn the structure. Next class, and the whole day on Thursday is going to be sparsity. So the first part is just going to be basic sparsity. The second part is going to be structure sparsity and potentially sparsity beyond vectors, so idea related to low rank and learning matrices with some sparse structure. But before that, we're going to meet tomorrow for the workshop, which is going to be here at some point in the morning. I have to say that it's quite impressive how between 9:30 and now, the numbers I see is pretty different. But hopefully for tomorrow morning, you can make an effort. I think Federico is the first. Huh? So Federico Girosi is a pillar of machine learning, so you should come see him. All right.